Yeah, thank you. And also thanks to the organizers for inviting me and scheduling my talk, first slot in the morning after the conference dinner. After the discussion we had in the business meeting yesterday, I decided to voluntarily shorten my talk by 5 minutes in the beginning. So, right. Okay, so you can tell from my title what the talk is about. But because I usually give very unstructured talks, this time I tried to have an outline in my talk, and maybe that makes it more structured. And if it's still too unstructured, just it's up to you to write the structure. So since this is like a general types audience, I'll have like a brief refresher on what infinity groupoids are, at least for me. And then I will talk about the problem that I've been interested in for many years, and for a long time thought there would be no positive solution. And then I'll talk a bit about what I think constitutes a solution, but you can check it for me. Right. So what are higher groupoids? If you're already a univalent mathematician, then there's no need to define this notion because it's just by definition a type. Every type already has the structure of an infinity groupoid. And then this would be a primitive notion for you, but then the content of the rest of the talk would be vacuous. So what I mean here is, suppose we start from sets, and we want to get from sets to higher groupoids. How would we do this? So intuitively, well, historically at least, people always said, well, a higher groupoid is a homotopy type. It's some sort of space up to homotopy equivalence. This is like the first picture I found on Wikipedia that didn't require me to put in a license. But I don't really like this because it brings point set topology into the picture, which I don't believe has any right to be there when you talk about higher groupoids, because for me this notion isn't really about topology in the point set sense. For me, it's more about this higher equivalence relation structure, this higher setoid structure. Most of you, since you know about types, will already know the setoid model, which appeared in many talks, actually, and also in discussions of many talks. But a higher setoid is just what you get when you kind of iterate setoids, so that the setoid valued relation itself has another setoid valued relation on top of it. So you have a set of points, set valued equivalence relation of, well, we call it equalities, I guess. And then this behaves like a groupoid, at least up to some notion of two equality. And then, well, you have coherences on each higher level, which I'm not going to write here. But intuitively, it's this sort of iterated structure that you're probably familiar with if you ever worked with the identity type in type theory. And like a concise way of describing this for higher category theorists would be to say that this is the infinity exact completion of the category of sets. So essentially what you get when you take the category of sets, or the higher category of sets, which is in fact like a truncated category in some sense, and then you close it under quotients, but quotient in the higher sense. So quotients under not just ordinary equivalence relations, but higher equivalence relations. So then the new objects are basically these sets equipped with higher equivalence relations. And this is like an informal definition because I have not specified what these dots are. And depending on how you do this, it can be more complicated or less complicated. And particularly this algebraic way of writing things suggested here has a nasty way of getting intractable rather soon if you don't pay attention. So the easiest, shortest way of actually defining what a higher setoid is precisely that I know is to just use this notion of Hahn semi-simplicial set. So I'm not going to define this in detail, but you can imagine it from this picture, which I again copied from Wikipedia. And it's just some formal gluing of points, lines, triangles, and so on. So this is actually, I think, from the page for simplicial sets, or maybe it was for simplicial complexes, I don't remember. But Semi-simplicial means that we don't care about degeneracies, if you know what degeneracies are. If you don't know what degeneracies are, you will get the right idea immediately. But yeah, so we don't just consider arbitrary such things. We require that we have some Kahn operation, which is called the horn filling operation. And that's because these triangles that are filled are actually witnesses that two edges compose to a third edge up to some two equality. So basically what this horn filling operation allows you to do is to find for every composable pair of equalities a transitivity equality. And well, you have this not just in dimension 2, but also in higher dimensions. And this is kind of responsible for giving you this higher coherence that I omitted in the previous slide. I guess I should keep track of the time as I always lose it. Yeah, so formally, the category, I like to have this rebellious notation delta plus, which algebraic topologists actually use for the augmented simplex category, but I like delta plus because it's the plus part of the Reedy structure on delta. And so it's finite sets, inhabited finite sets, I should say, and injections. And then we consider the full subcategory of those which come equipped with a Kahn operation. So the Kahn operation is structure. That's important because I actually want to avoid existential quantifiers in my meta theory completely. So these higher quotients that I'm taking as sets, since it's always going to be about set valued relations, I'm never going to be forced to take any sort of strict quotient. Whenever I want to do some higher quotient, I just add identifications at the next level without ever strictly identifying things at the original level. So the meta theory is actually very weak. So there are no quotients whatsoever. Right. Since no one interrupted me, everything is totally clear so far, right? Yeah, you got the wrong intuition from the picture, Ulrich. But yeah, okay, I didn't find the picture in my 5-minute search that had arrows. Yes, okay, I looked at the picture and I actually got the wrong mistake. Yeah, so it's finite inhabited linear orders and order preserving maps. Yes, very good. Otherwise, this is all wrong. Okay. So this has been analyzed constructively already. So if you're more familiar with the Kahn model structure on simplicial sets, Simon Henry has shown that the two are constructively equivalent. He has this nice framework of weak model structures that work completely constructively, and also all these notions of plane equivalence is generalized to that setting. So constructive, all very nice. So this essentially fits with the standard notion of Kahn simplicial sets. So this is my symbol for presheaves in this talk, because presheaves are a generalization of power sets, right? So I just write P. Right. It's not. It's what I forgot to write here. It's inhabited. Yeah. Right. So based on this, from this picture here, we can see actually some properties that our desired notion of a groupoid has, which will be important when we try to build models of hot that are supposed to model this. One of which is that if we restrict to zero truncated infinity groupoids, we want to recover the homotopy theory of ordinary setoids. The second property that I singled out here is that contractibility of families can be tested pointwise. So this is like very similar to the internal definition of equivalences in hot. But here, when I say point, I really mean external point, so an element of x0, of the set x0. So if I have, are these, can I draw on these boards? Okay. Yeah, I guess I don't have time anyway. But so if we have a map between higher groupoids, and I know that every fiber of this map over every point is contractible, then I want to know that this is in fact an isomorphism. Thank you. yeah, for the future, I guess. Yeah, so in particular, we want to have what I call the pointwise principle, which is that a family of H propositions should already be true if it has a section on points. So there should be no coherence to verify. If I have a family of H propositions, it should be enough to find for every point in the base a point over it, because finding witnesses of relatedness should be taken care of by the family being a family of H propositions. And the reason why I'm stressing these properties so much is that they actually fail in most of the cubical models that have been developed. It's quite infuriating, really. Yeah, and what I said about propositional truncation was, already said earlier, when you truncate, you never really do any strict identifications, you just add high identifications so the points stay the same. So in particular, this implies that you have choice for discrete groupoids. This was already discussed after an earlier talk, that in setoids you have choice for discrete setoids. So the same holds true in the higher setting, or should hold true. So you can see it as a correctness criterion. And related also presentation, every high groupoid is covered by a projective one, because the projective ones are exactly going to be those that are equivalent to discrete ones. And every groupoid is covered by its set of points. Okay, so we know from early work by people, one of which is here, that in type theory, if you have identity types, Martin-Löf identity types, you can actually recover the data of an infinity groupoid from every type. And maybe now I can try out this fancy new technology. Yeah. Oh, this is the future. Yeah, so we know very well that if you have equalities in type theory, my eyesight is also deteriorated. Oh, wow. Okay. Yeah, so I mean, if I have these two things, then I can produce a composite equality x equal z using whatever J elimination. I'm not going to write it out, whatever. And in fact, this has the structure of a groupoid up to equality between equalities and so on. So exactly this kind of data we saw before. So these guys use some more algebraic notion of higher groupoids, but it will be constructively equivalent to Kant semi-simplicial sets. Is my talk already over?
No, I'm not taking the chat.
Great. All right. So this is constructive. If you're a traditional mathematician that likes to start from sets, this tells you how, from type theory, you get infinity groupoids. But this is the segue for the main topic of the talk, namely the converse question: can we do it in the other way around? Can we take groupoids built from sets and interpret type theory in that? So if you know anything about HOT, then you know that the answer is yes, because that's what Wolowski did with his simplicial set model. The only thing that I complain about in this talk is that it's not effective. So the interpretation is not constructive. You cannot execute it. The reason is basically failure of every simplicial set of simplicial sets to generally be cofibrant, to be able to have cell complex presentations of simplicial sets. So the question of this talk, and I don't know, this question that has vexed me since I started thinking about these things back when I first came to Gothenburg as a postdoc, I guess, is if we can effectively interpret HOT in infinity groupoids. And I always thought, after trying, that the answer must be no. I tried like manually setting up just some interpretation in some algebraic definition of two groupoids, and every time local Cartesian closure was the problem, because it's very hard to find models in which pi types actually modeled strictly, because we need definitional beta and eta for at least a book model of HOT. But yeah, if you're willing to weaken this question to some version of HOT that does not have all the usual definition equalities, then this problem may have actually already been solved. So this slide took me the longest to prepare. You don't seem to impress, but okay. So this is an overview of all the kinds of models that I'm aware of that people have proposed for HOT. Let me know if I'm missing your model. So there was the original simplicious set model by Vogotsky, written up by Kapulkin and Lumsdain. Yeah, it presents infinity groupoids, but it's not constructive. Then Thierry Cocon and co-workers very early on tried semi-simplicious sets because generally these are the problem with cofibrancy in simplicious set. And well, they were not quite able to get interpretation of HOT. There were problems with strict pi types and substitutional coherence, so they gave up and switched to cubical sets. But later, some people went back to simplicious sets and started working on what they apparently call effective confibrations. And Benno here knows more about this than I do. But as far as I know, it's not yet known to be a model of HOT. How likely would you say that it will be? Very likely. Okay, I will put it in the slides. Yeah, but actually, my gripe with this would not be that it's not a model of HOT, but I'm not sure if it actually presents higher groupoids constructively. So the proof that you have that compares it with confibrations is classical. So, and basically this already shows one of the problems that we are going to have when we compare our fibrations in these models with the confibrations in simplicious or semi-simplicious sets before. Here the fibrations typically come with some strength and uniformity properties. And it's kind of quite hard to equip just like a random setoid or higher setoid fibration with the uniformity required to make it a type in one of these models. Right, so then Gambino and Henry looked at cofibrant simplicious sets, but there are coherence issues there and also issues with pi types. And then there's this whole trend of cubical models. So this is kind of the biggest class of models. I grouped them here all together, but it started quite early. So BCH was the first generation, then came CCHM, and then came ABC FHL in various combinations. And well, all of them are constructive models of HOT. So this was kind of the first way of getting a constructive computational interpretation of univalence. But it turned out that actually the homotopy theory of these models is quite far sometimes from presenting higher groupoids. So naively, one might expect that the two goals of computationally interpreting univalence and modeling higher groupoids should kind of agree, but I think this demonstrates that they are kind of orthogonal to each other. So what's lacking in these cubical models is that the base category is basically not a ready category, if you know what that means, which makes it impossible kind of to analyze the objects by induction on dimension. There's not a well-behaved notion of dimension, even though you might think that cubes have a well-behaved notion of dimension. So this is at least here a generalized 3D category, but that's already enough to cause problems. And then there are adaptions later on, equivariant cubical sets and one connection cubical sets. So in these two collaborations, we kind of modified some of these models to make it so that at least classically higher groupoids are presented. But I'm not happy with this because the proof that it's equivalent to, let's say, Kahn-simplicious sets is hopelessly classical. So it's the same problem as with effective confibrations. You need next to the middle. Otherwise, there's no choice and no way to get the induction going, basically. Yeah, how much time have I wasted? Oh. Yeah, so I was expecting a negative answer. The core problem is that, or one of the core problems is kind of like whack-a-duck problem, or how do you say? Whack-a-mole, quack-a-duck, or whatever it's called. So one of the holes is that you want fibrations to be closed under push forward. So you want push forward in your P-shift category to preserve fibrancy of types. And since you're working with this, well, since contexts have to be cofibrant in models of type theory because how we interpret trivial fibrations. Essentially, this always seems to require some sort of uniformity, and it's hard to get uniformity from biaceroid fibrations or whatever. Okay, so that's the negative part of the talk, and now the positive. So I propose that you can take certain cubical models. So these are the conditions that have to be satisfied for this to work. You can work with the second generation or third generation model. It has to be a cube category that fully faithfully extends the simplex category. For example, the idempotent completion of the CCHM cube category. The interval object has to have connections, and the cofibration classifier has to classify simplex boundaries. So simplex boundaries coming via left-Kahn extension along J. And then, of course, all the assumptions, the kind of the Orton-Pitts axiom have to be satisfied, or whatever the ABC FHL axioms have to be satisfied for these models to exist. But yeah, you can take these two examples. The first one kind of corresponds to freely generated distributive lattices, and the second one to finitely presented non-trivial distributed lattices. Okay, so I don't have time to go into all the details. So scream if you wanted to know a particular detail, but I'm just going to give a high-level overview. So first of all, because we have this fully faithful inclusion of delta into the cube category, we have some sort of reflective, or I guess this is actually, yeah, so this is a reflective embedding of simplicious sets into cubical sets. And then we have a further adjunction between semi-simplicious sets and simplicious sets. And that one we already know is constructively quite well behaved. So this is actually a Quillen equivalence here. So consider just the composite. So M is the name for this composite. And let's just look at the composite adjunction here. So I don't know how to directly analyze the adjunction with simplicious sets. I really have to go to semi-simplicious sets. And then the claims are basically that both of these functors are algebraic right Quillen functors. So algebraic and parenthesis, because by default, I always work with structured notions. So right Quillen is always, well, okay, I'm not going to get into this. This is constructivity issues. So essentially, this means that they preserve fibrancy and trivial fibrancy, so that if you have a type in here, it's still a type in here, and also for contractible types. And well, second, this should be a Quillen reflection. This is not too difficult once you have this, because you already know that simplicious sets strictly reflectively embed into cubical sets, and then, well, you know that the comparison between simplicious and semi-simplicious sets is a Quillen equivalence. And the last thing that you would have to check is that this induced Lex modality M, so the composite of these two functors on cubical sets, is a Lex modality in the sense of Reikes, Bitter, Schumann. And the most surprising of these is actually the first one. So for some reason, since we are dealing here kind of exclusively with presentation issues, not with issues of the presented higher category, it's always about the fibrations as opposed to some question about the weak equivalences. So if all of these are true, then quite formally, the localization of this at the modality will be given by, or the homotopy or the localization of this will be given by Kahn semi-simplicious sets. Retrospectively, it looks like quite obvious to write down these adjunctions and ask yourself these questions. But when you start working with these functors, most of the functors you write down fail to produce uniform fibrations from non-uniform fibrations. And it's kind of magic, for me at least, that this M lower star here magically lands in uniform Kahn fibrations. It gets uniformity out of nothing. And my goal for this talk is to somehow explain to you why that is the case. it's really suspicious that no one has asked a question so far. That means that something is wrong. Maybe I'm not speaking loud enough.
It's too early.
I agree. That's what's wrong. Okay, so the surprising part is the first one. And another mistake that I see people that go from type theory to semantics often make is they start with the types. In homotopy theory, it's always easier to first look at the trivial fibrations, the contractible types. And then usually you can derive something about the types as a corollary. So let's first convince ourselves that these two functors here preserve trivial fibrations. If you know what trivial fibrations are in these two models. So here's a diagram that is supposed to convey the intuition. So there's no pointer, but is there maybe a stick? Oh, wow. Cool, thank you. And how do I use it? Amazing. Right, so this is the adjunction from before. Don't look at my shaky hand. And here I drew some various classes of trivial fibrations. So everything in the top row lives in cubical sets, and everything in the bottom row lives in semi-simplicial sets. In cubical sets, I distinguish between the uniform trivial fibrations. So this is those maps that lift against the category of generating trivial generating cofibrations, essentially the category of maps classified by the cofibration classifier. This is just Kahn fibrations, trivial Kahn fibrations. It's kind of created by M upper star from the semi-simplicial ones, because by definition it's just lifting against left Kahn extension of the simplex boundaries along M. So this is doing nothing. And then what's happening in semi-simplicial sets, what's special about semi-simplicial sets is that they are a garden of uniformity. So magically in semi-simplicial sets, ordinary trivial Kahn fibrations, so those are maps that lift against boundary inclusions. I can maybe draw here like, no. I don't really know if I want to switch back and forth, so maybe I don't. So we had these horn filling conditions. A simpler condition is a so-called boundary filling condition, which is that in your semi-simplicial set, every time you have a boundary of some n simplex, you can find a filler. So if you can do this in every dimension, that basically means that your semi-simplicial set is contractible in some sense. And there's like a relative version for maps, which is kind of what's going on here. And right, so we have to explain why lifting against boundary inclusions makes it so that you can uniformly lift against level-wise decidable inclusions in semi-simplicial sets. But in fact, there's always a universal lifting problem for these uniform trivial fibrations, which encapsulates all these lifts together with the uniformity condition in terms of just a single retraction in a certain factorization. So you take the partial map factorization and you look for a retract in there. And the map that you have to do this for is a level-wise decidable inclusion. In particular, you can decompose it as a cell complex. So you can decompose this universal map, and that's enough. In simplicial set, this wouldn't work, because in simplicial sets, a level-wise decidable inclusion is not necessarily a cell complex of boundary inclusions. It's really important that we don't have degeneracies here. And then formally, right Kahn extending makes uniform trivial fibrations in semi-simplicial sets into uniform trivial fibrations in cubical sets, just because restriction preserves level-wise decidable inclusions, which are the cofibrations in both settings, if I make suitable simplifying assumptions on my cubical set model. Right. So this is the trivial fibration picture, and now we go to the fibration picture, which is a bit more involved, but you can reduce it to the trivial fibration picture. So first, you start with a uniform fibration in cubical sets, and you forget that it was uniform. So it's just a Kahn fibration now. You restrict it to be a semi-simplicial Kahn fibration. In semi-simplicial sets, we can apply the Gabriel-Zisman lemma that also works in semi-simplicial sets, just as it does in simplicial sets. that relates Kahn fibrations with filling fibrations. If you know about filling boxes, here it's filling prisms, but with respect to the geometric monoidal structure, not the Cartesian one. And equivalently, you can define a filling fibration as something such that if you apply the pullback internal hom with the endpoint inclusion of the line, you get trivial fibrations. So actually, they are created by a very simple functor from the trivial fibrations in semi-simplicious sets. And for those, we have already shown that being a trivial fibration implies being a uniform trivial fibration. So you can transpose this over to derive that actually being a filling fibration also makes you a uniform filling fibration. And then curiously, you can't just apply M lower star directly and observe that you get a uniform fibration on the other side. You first have to forget that it was a filling fibration and only remember the composition part. And the composition part you can transpose over. That has to do with the fact that the monoidal product with the interval in semi-simplicious sets and the Cartesian product on the cubical side are not compatible in the right way that you would need for this. But if you only restrict to the other side, then you can transpose. Yeah, so yeah, I said all of these in words. These are all different classes. Just ask if you want to have more details, but you're all too tired and sleepy, so no one is actually listening. Are you listening?
Maybe. Should it be F unit? Should it be F unit?
I don't know where you have this attention, but yes, you managed to read until the end of the diagram. That should be a F unit, yes. So this is essentially the modality. Restricting along M and right Kahn extending, what we want to make sure is that it preserves fibrations and trivial fibrations. So once we do this round trip, we have to make sure that we again get a uniform fibration, which is what we started with. Yeah. Okay, so that's the interesting bit, I would say, or the surprising. For me, this was the surprising bit, especially this garden of uniformity trick. And then there's like a minor bit of combinatorics also involved in verifying that it's Lex modality. So some of it is quite formal, and you can use some results that we proved earlier in a paper with Fabien Rouch and Thierry Coquin on Lex operations. But essentially, you're going to have to witness at some point, this also relates to two, that in the adjunction between semi-simplicious sets and simplicious sets, if you look at the monad induced on simplicious set, this is idempotent in a homotopical way, witnessed in a very strong sense by an elementary homotopy. So it's important that this is algebraic, that it's not just level-wise, because otherwise we get into coherence problems later on when we use this to interpret type theory. So when we work with homotopical notions here, it's always important that it's always phase change stable. Everything here is stable in a substitution. That's why I'm writing these algebraic things here, if you know this. Okay, so that's this. And this is all the details that I managed to write in the slides before I fell asleep for this part. But I'm willing to give you more details on paper here with this if you want to see it. So then you can check that all these desired axioms hold in this model. So this pointwise principle that a type is contractible, or if it's contractible over every point, in particular proposition, is contractible already if it's inhabited over every, if it has a section, pointwise section. Choice for discrete things, so in particular countable choice. So discrete here means that it's strictly modal for the exponentiation with the interval or whatever, but equivalently, yeah, whatever. Dependent choice is, I guess, not a consequence of the discrete choice thing, but it still holds, presentation axiom holds. And because we are starting from a cubical base model and the modality that we're localizing at is actually quite nice if you write it out. So it's not an accessible modality, or I don't know how to see it as an accessible modality, but it is good enough in these ways that we typically work with modalities in settings where we don't have accessibility. So essentially, the functor is given by restriction and right-Kahn extension. It's a strictly positive operation if you go outside of the presheaf category. So it's some kind of indexed polynomial functor. And if you want to interpret high inductive types, you just take a simultaneous high inductive type for being modal for this modality, which is a strictly positive constructor. It's just a patch operation. And then the usual constructor for your high inductive type. So this is very similar to what we did in the CRS paper for the Kobar modality. Yeah, so that's similar to this. And this is not for the slides, so I have to go here. Yeah, so I hope there are applications. I mean, the longer I work with something, the more I forget why it's important. I don't know. This is like, I feel like an imposter when I write this, but I guess it's useful to build. I mean, once you have a correct base model, you can build correct higher topos models, and you can, I don't know, do constructive models for synthetic stone duality and improve the models that we already have for synthetic algebraic geometry. We can also use the work that Ulrich and others have been doing in simplicial type theory to get constructive models of simplicial type theory, including their variation in higher categories constructively, which I guess was unclear before. And when Andrew Swan visited me a couple of weeks or a month ago, he told me that it's apparently also useful for some higher realizability, but I don't know anything about that. Yeah, so please tell me there are more applications. Okay, so amazing. I'm in time. Right. Yeah.